Every part of you, every element heavier than hydrogen was created inside stars. The calcium in your teeth, the iron in your blood, these atoms were born in the heart of ancient suns. When stars die, they scatter their insides across the cosmos, seeding new stars, planets, and life. In a very real way, you are made of stardust. The universe's story is not just out there, but within us all. Let's begin our journey to discover how the universe recycles itself and how we are all children of the stars. The universe is alive with stars being born, shining, and dying. When stars die, they return their elements to space, a process called cosmic recycling. This cycle shapes everything: dust, planets, oceans, and life itself. The water you drink, the air you breathe, even the gold in a ring, all forged in ancient stars. Without this recycling, Earth would be barren. The death of a star is the origin of everything we are. The universe is a master recycler, and we are its extraordinary creation. Every star begins in darkness, inside vast cold molecular clouds, stellar nurseries. These clouds, stretching for light years, are filled with hydrogen, helium, and dust, remnants of dead stars. Though they appear empty, they hold the ingredients for new stars and planets. Turbulent forces shape the gas and dust into dense knots. Within these knots, the seeds of future stars lie dormant, waiting to collapse and ignite. Without these nurseries, the universe would be empty. Here, the ashes of old stars become the building blocks of new ones. Every star's story starts in the silent expanse of a molecular cloud. Gravity pulls dense pockets of gas and dust together inside molecular clouds. As these clumps contract, they spin and flatten into swirling disks. At the center, a hot core forms, a protostar, glowing dimly from gravitational heat. The protostar grows by accreting matter, sometimes blasting jets of gas from its poles. If it gathers enough mass, it will ignite. If not, it fades as a brown dwarf. For millions of years, protostars remain hidden in dust, but infrared telescopes reveal their birth. Gravity sculpts cold dust into the glowing heart of a future star. As the protostar contracts, its core heats up to millions of degrees. When it reaches about 10 million Kelvin, hydrogen atoms fuse into helium. Nuclear fusion begins. This releases immense energy, balancing gravity and halting collapse. A star is born, emerging from its cocoon to shine for billions of years. Smaller stars fuse hydrogen slowly. Massive stars burn fuel rapidly. This marks the star's entry into the main sequence, the longest, most stable phase of its life. The universe fills with light, warmth, and the potential for life. With fusion ignited, the star enters its main sequence, the prime of its life. Gravity and fusion energy balance perfectly, allowing the star to shine steadily for billions of years. Our sun is in this phase, providing stable warmth for life on Earth. The core slowly changes as hydrogen becomes helium, making the star brighter over time. Most stars in the night sky are in this stable phase. However, this stability is temporary. The hydrogen fuel will eventually run out. When that happens, the star's life will undergo a dramatic change. The main sequence is the quiet engine of the cosmos. A star's mass determines its entire life story. Low-mass stars, like red dwarfs, burn fuel slowly and live for trillions of years, fading quietly. Massive stars burn bright and fast, living only millions of years before dying spectacularly. Sun-like stars provide stable conditions for life. Massive stars create and spread heavy elements. Both types are essential to the universe's evolution. Mass sets a star's fate, a gentle fade or a brilliant explosive end. The diversity of stars shapes the cosmos and everything within it. In the end, every star's journey is written by its mass. While a star on the main sequence is primarily fusing hydrogen into helium, this is not the only alchemy taking place within its fiery heart. The process of fusion itself begins the grand cosmic project of element creation. It is during this long, stable phase that stars start to produce some of the key ingredients necessary for life. Even the simplest fusion reaction, turning hydrogen into helium, is a step up the elemental ladder, creating a new substance from the universe's most basic building block. This is just the beginning of the star's role as a cosmic factory. In stars more massive than our sun, the fusion process is more complex. They use a different mechanism known as the CNO cycle. This stands for carbon, nitrogen, and oxygen. In this cycle, these three elements act as catalysts. They are not consumed in the reaction but are used to help fuse hydrogen into helium much more efficiently and at a much higher rate. The presence of carbon, nitrogen, and oxygen, themselves forged in an earlier generation of stars, allows these massive stars to generate the incredible amounts of energy that makes them shine so brightly. The CNO cycle is a beautiful example of cosmic recycling in action. The very elements that are crucial for life as we know it, carbon, the backbone of organic chemistry, nitrogen, a key component of DNA, and oxygen essential for respiration, are actively participating in the life of a star. While the star is on the main sequence, it is not yet creating large new quantities of these elements. However, it is demonstrating their importance in cosmic processes. The star is using the ashes of its ancestors to power its own life, a hint of the deeper recycling to come. This process sets the stage for what will happen later in the star's life. The steady production of helium in the core is building up a new fuel source for the next phase of fusion. The main sequence is not just a time of stability, it is a period of preparation. The star is slowly but surely changing its internal structure, creating the conditions that will eventually lead to the forging of even heavier elements. The prime of a star's life is a creative time, laying the elemental groundwork for future stars, planets, and ultimately, for us. After billions of years of steady, reliable fusion, a star like our Sun finally faces its first great crisis. The vast reservoir of hydrogen fuel in its core, which has powered it throughout its long main sequence life, begins to run out. The nuclear furnace at the star's center starts to sputter and fade. Without the outward pressure from fusion to counteract the relentless inward pull of gravity, the delicate balance that defined its adulthood is broken. Gravity begins to win the cosmic tug-of-war, and the star's core starts to collapse under its immense weight, marking the beginning of the end. This core collapse triggers a dramatic and counterintuitive transformation. As the core, now composed mainly of inert helium ash, contracts and becomes denser, its temperature skyrockets. This intense heat radiates outwards into the surrounding shell of hydrogen that was previously too cool to undergo fusion. Suddenly, this shell of hydrogen ignites, burning with a ferocious intensity. This new shell-burning phase produces far more energy than the core fusion ever did. This immense flood of energy pushes the star's outer layers dramatically outward, causing them to expand to enormous proportions. The star begins to swell, growing 100 or even 1,000 times its original size. As its outer layers expand, they also cool down, causing the star's color to shift from a brilliant white or yellow to a deep, ominous red. The star has transformed into a red giant. It is now a bloated, luminous behemoth, a pale and distorted shadow of its former self. If our own sun were to become a red giant, its expanding atmosphere would engulf the orbits of Mercury, Venus, and possibly even Earth, scorching our world to a cinder. This is the fate that awaits our solar system in about 5 billion years. Despite its colossal size and intimidating appearance, a red giant is a star in its death throes. Its expanded outer layers are tenuous and wispy, far less dense than the star it once was. The star has entered a new, unstable, and ultimately temporary phase of its existence. It has embarked on a new journey of elemental creation, but it is a path that leads inexorably towards its final demise. The quiet, stable life of the main sequence is over, replaced by a turbulent and spectacular decline that will forever change its destiny and enrich the cosmos around it. Deep inside the bloated red giant, the contracting core continues to heat up, under the crushing force of gravity. It is a crucible of helium ash, squeezed to unimaginable densities and temperatures. For millions of years this core remains inert, while the hydrogen shell above it rages, but as the temperature climbs, it approaches another critical threshold, 100 million Kelvin. At this staggering temperature, the helium nuclei, which had previously repelled each other, are slammed together with enough force to overcome their repulsion and fuse into something new. The star has found a new source of fuel. In a cataclysmic event known as the helium flash, the entire helium core ignites in a matter of minutes. This fusion process, called the triple alpha process, is a remarkable feat of cosmic alchemy. 3 helium nuclei, also known as alpha particles, combine to form a single nucleus of carbon. This process releases a tremendous amount of energy, briefly stabilizing the star once more. Some of this newly created carbon can then fuse with another helium nucleus to form oxygen. For the first time, the star is creating the fundamental elements of life, carbon and oxygen, in significant quantities. This new phase of core fusion causes the star to shrink slightly and become hotter, leaving the red giant branch for a time. It is a temporary reprieve, a second adulthood powered by a new fuel source. However, helium is a far less efficient fuel than hydrogen, and this phase lasts for a much shorter time. perhaps only a few million years. The star is now burning through its remaining resources at an accelerated rate. It is in a race against time, forging heavier elements in its core while its ultimate fate looms ever closer. The creation of carbon and oxygen inside red giants is one of the most important events in the story of cosmic recycling. These are the elements that form the backbone of organic molecules, the building blocks of planets, and the very substance of life itself. Without this phase in the life of low-mass stars, the universe would be critically deficient in these life-giving materials. The red giant, in its slow decline, is performing one of its most vital functions, manufacturing the raw materials for future generations of cosmic creation. The star's second life, burning helium in its core, is destined to be short-lived. Eventually the helium fuel also runs out, and the core, now made of carbon and oxygen, begins to contract once more. For a star the size of our Sun, gravity is not strong enough to ignite carbon fusion. The star has reached the end of its line. It can no longer generate energy at its center. The nuclear furnace is extinguished for good. With the core dead, the star enters its final, most unstable phase, driven by erratic bursts of fusion in the shells surrounding the core. These final desperate gasps of fusion are known as thermal pulses. They are violent and unpredictable, generating enormous bursts of energy that push the star's outer layers away from the core. With each pulse, the star sheds a significant portion of its mass, puffing its atmosphere out into the surrounding space. Over thousands of years, the star ejects its outer envelope in a series of gentle, expanding waves. This material, enriched with the carbon, oxygen, and other elements forged within the star, drifts outward to form a vast, glowing cloud. This beautiful, expanding shroud of gas is known as a planetary nebula. The name is a historical misnomer. They have nothing to do with planets. Early astronomers, viewing them through small telescopes, thought their round, hazy shapes resembled gas giant planets. What they were actually seeing was the swan song of a dying star. The intricate shapes and stunning colors of planetary nebulae, like the famous Ring Nebula or Helix Nebula, are created as the ejected gas is illuminated by the intense ultraviolet radiation from the hot, exposed core left behind. At the center of this celestial artwork lies the star's final remnant, a white dwarf. This is the incredibly dense, Earth-sized core of carbon and oxygen, no longer undergoing fusion. It is a stellar ember, glowing with residual heat, that will spend the next trillions of years slowly cooling down and fading into blackness. The star's life is over, but its legacy is just beginning. It has gently returned its precious, newly forged elements back into the cosmic environment, providing the raw materials for the next cycle of birth. For stars born with more than 8 times the mass of our Sun, the journey of element creation does not end with carbon and oxygen. Their immense gravity is powerful enough to ignite fusion in heavier and heavier elements, triggering a frantic sequence of burning stages deep within their cores. After exhausting the helium in its core, the massive star begins to fuse carbon into neon and magnesium. When carbon runs out, the core contracts and heats up further, igniting neon, then oxygen, and finally silicon. Each of these burning stages lasts for a shorter and shorter period. Carbon fusion for centuries, neon for years, oxygen for months, and silicon for just a single day. This frantic race against gravitational collapse creates a unique structure within the star, resembling a cosmic onion. At its center lies the final product of this fusion chain, surrounded by concentric shells of silicon, oxygen, neon, carbon, helium, and an outer envelope of hydrogen. Each shell contains the fuel for the layer beneath it. The star has become a multi-layered nuclear reactor, desperately trying to hold itself up against its own colossal weight. But this desperate struggle is leading it towards an inescapable and catastrophic dead end. The heart of the star is about to produce an element that will seal its fate. The final stage of this fusion cascade is the burning of silicon, which produces the element iron. Here the laws of nuclear physics deliver a fatal blow. For all elements leading up to iron, the process of fusion releases energy, which provides the outward pressure needed to support the star. However, iron is the most stable atomic nucleus in the universe. Fusing iron atoms does not release energy, it consumes it. The star has effectively produced a core of ash from which no further energy can be extracted. The nuclear furnace at the heart of the star has been extinguished forever. With its energy source gone, the iron core is left with no defense against the crushing force of gravity. In a fraction of a second, the star's fate is sealed. It has reached the ultimate dead end. The core, now powerless, can no longer support the crushing weight of the star's outer layers, which weigh more than our entire sun. The star, which shone brilliantly for millions of years, is now poised on the brink of a cataclysmic collapse. The most violent event in the universe is about to be unleashed, an explosion of unimaginable power that will change the cosmos around it. The iron core, now inert and unsupported, succumbs to gravity in an instant. The collapse is astonishingly fast. The core, which might be the size of the Earth, shrinks down to the size of a city in less than a second, accelerating inward at speeds reaching a quarter of the speed of light, over 70,000 kilometers per second. As the core implodes, the pressure and density become so extreme that they defy comprehension. Protons and electrons are squeezed together with such incredible force that they merge, forming a sea of superdense neutrons. The star's very atoms are crushed out of existence. This rapid collapse continues until the core becomes as dense as an atomic nucleus itself. At this point, the neutrons can be compressed no further. The core becomes unimaginably rigid and stiff, and the collapse comes to an abrupt and violent halt. The material that was still raining down from the outer layers crashes onto this newly formed, unyielding neutron core and bounces back with tremendous force. This rebound creates a colossal shockwave that begins to propagate outward, rocketing through the star's outer layers. The stage is set for a supernova. As this shockwave tears through the star, it heats the surrounding material to billions of degrees, triggering a final fleeting burst of explosive fusion. This is known as explosive nucleosynthesis. In the chaotic, energy-rich environment of the explosion, atomic nuclei are bombarded with a blizzard of free neutrons. This rapid neutron capture process, or R process, is the only known way the universe can create elements heavier than iron. In these fiery moments, the cosmos forges the rarest and most precious materials in existence, including silver, platinum, gold, and uranium. The shockwave, supercharged with energy from this final burst of fusion and a flood of ghostly particles called neutrinos, finally rips the star apart in a titanic explosion. For a few weeks, the supernova can outshine its entire host galaxy, releasing more energy in an instant than our sun will in its entire 10 billion-year lifetime. The star's life ends not with a whimper but with the most spectacular bang in the universe. It sacrifices itself, but in doing so, it seeds the cosmos with the heavy elements necessary for building rocky planets and creating complex life. While the core collapse of a massive star is the most common way to create a supernova, it is not the only one. The universe has devised another, equally spectacular method for stellar detonation, one that involves the death of a much smaller star. This second path leads to what astronomers call a type Ia supernova. It occurs not with a single massive star but in a binary star system where two stars orbit each other closely. One of these stars must be a white dwarf, the dense carbon-oxygen remnant left behind by a star like our sun. In this cosmic dance, if the white dwarf's companion star is close enough, the white dwarf's powerful gravity can begin to pull material, mostly hydrogen and helium, from its partner. Over thousands or millions of years, this stolen matter accumulates. On the surface of the white dwarf, it gradually increases its mass. The white dwarf, an object that should have been quietly fading into obscurity, is instead being pushed toward a violent end. It slowly approaches a critical mass limit known as the Chandrasekhar limit, which is about 1.4 times the mass of our sun. Once the white dwarf crosses this threshold, gravity overwhelms the forces supporting it. A runaway chain reaction of carbon fusion ignites throughout the entire star, almost simultaneously. The result is a thermonuclear explosion of unimaginable power that completely obliterates the white dwarf, leaving nothing behind. Because these explosions always happen when the white dwarf reaches the same critical mass, they are remarkably consistent in their brightness. This makes them incredibly useful tools for astronomers, who use them as standard candles to measure the vast distances across the universe and study its expansion. These different types of supernovae produce distinct mixtures of elements. Core collapse supernovae are the primary source of elements like oxygen, silicon, and iron, while type Ia supernovae produce enormous quantities of nickel, which then decays into the iron we see in the explosion's aftermath. Recent research has also highlighted other explosive events, such as the collision of two neutron stars, which creates a kilonova. These events are now thought to be the dominant source of the very heaviest elements like gold and platinum. The universe, it seems, has a diverse and violent toolkit for cosmic recycling. When a massive star explodes in a supernova, its outer layers are blasted away, but the collapsed core often survives. This is the remnant left behind, an object of such extreme density that it challenges the imagination. If the original star was massive but not overwhelmingly so, the core will stabilize as a neutron star. This object is essentially a giant atomic nucleus, composed almost entirely of neutrons packed tightly together. It is a city-sized sphere, perhaps only 20 kilometers in diameter, yet it contains more mass than our Sun. The gravitational force on its surface is hundreds of billions of times stronger than on Earth, crushing every feature into a nearly perfect sphere. The density of a neutron star is simply staggering. A single teaspoon of its material would weigh billions of tons, as much as a mountain. This is matter at the absolute limit of compression, where the very structure of atoms has been destroyed and only a sea of neutrons remains. The star's original magnetic field has also been compressed into this tiny volume, creating a magnetic field trillions of times more powerful than Earth's. Born from the ashes of a violent explosion, the neutron star is one of the most extreme and exotic objects in the entire universe, a testament to the incredible forces unleashed during a star's death. Many of these neutron stars are born spinning incredibly rapidly, a consequence of the conservation of angular momentum from the original, much larger star. As they spin, their powerful magnetic fields can channel beams of radiation, like radio waves, out from their magnetic poles. If these poles are not aligned with the star's rotational axis, the beams sweep across the cosmos like a celestial lighthouse. If one of these beams happens to sweep past Earth, our radio telescopes detect a regular repeating pulse of energy. We call these objects pulsars. They are the ticking clocks of the cosmos, remnants of a supernova that continue to announce their presence across the galaxy. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and for a time the regular signals were humorously labeled LGM-1 for little green men, as their perfect regularity seemed almost artificial. We now know they are the natural, breathtaking result of a star's death. Over time, a pulsar will slowly lose energy and spin down, its lighthouse beam fading over millions of years. But in its youth, it is a powerful beacon, a spinning, super-dense tombstone that marks the grave of a once mighty star, while also serving as a precise tool for astronomers to study the fabric of space itself. There is, however, a final, more mysterious fate for the most massive stars in the universe. If the collapsing core of a supernova is exceptionally massive, more than about 3 times the mass of our Sun, then nothing in the known universe can stop its collapse. Not even the immense pressure of densely packed neutrons is strong enough to resist the ultimate triumph of gravity. The core continues to shrink, collapsing past the point of being a neutron star. It contracts relentlessly, crushing all its mass down into an infinitely small point of zero volume and infinite density. At this moment, a black hole is born. A black hole is not a hole in the traditional sense, but rather a region of space-time so warped by gravity that nothing, not even light, can escape it. It is the ultimate cosmic prison. Surrounding this central point, known as the singularity, is a boundary called the event horizon. This is the point of no return. Any matter or energy that crosses the event horizon is forever trapped, pulled inexorably toward the singularity at the center. From the outside, the event horizon appears as a perfect sphere of blackness, a shadow cast upon the universe, hiding the incomprehensible physics that lie within its grasp. The birth of a black hole represents the complete and total victory of gravity over all other forces of nature. It is the endpoint of matter as we know it, a place where our understanding of physics breaks down completely. The star's substance is not recycled back into the universe in a gentle puff or even a violent explosion. Instead, it is removed from the visible cosmos, its mass now contributing only through its immense gravitational pull on the space around it. The star that once lit up the galaxy has become a vortex of pure gravity, warping space and time itself into a knot. For a long time, black holes were purely theoretical concepts, predictions of Einstein's theory of general relativity. Today, we have overwhelming evidence of their existence. We can observe stars orbiting these invisible massive objects, and we can see the intense radiation emitted by gas, as it is heated to millions of degrees before falling past the event horizon. In 2019, the Event Horizon Telescope collaboration captured the first ever direct image of a black hole's shadow, making these enigmatic objects stunningly real. They are the dark, silent remnants of the universe's most colossal stars. For decades, astronomers believed that supernovae were the sole cosmic forges for the heaviest elements. However, a groundbreaking discovery in 2017 revealed another, even more spectacular source. On August 17th of that year, the LIGO and Virgo gravitational wave observatories detected ripples in spacetime from a cataclysmic event 130 million light-years away. For the first time they had witnessed the final violent moments of two neutron stars spiraling into each other and merging. Telescopes around the world quickly turned to the source, capturing the explosive aftermath of this collision, an event known as a kilonova. A kilonova is an explosion that, while less bright than a supernova, is a powerhouse of element creation. As the two city-sized super-dense neutron stars collide, they rip each other apart, flinging a massive cloud of pure neutron-rich matter out into space. This ejected material provides the perfect conditions for the rapid neutron capture process, or R process, to occur on a massive scale. In this chaotic environment, neutrons are rapidly absorbed by atomic nuclei, building them up into the heaviest and rarest elements in the universe, far more efficiently than even a supernova can. The light from this kilonova, designated GW170817, carried the unmistakable chemical fingerprints of heavy elements. Spectroscopic analysis revealed the presence of vast quantities of gold and platinum being created in real time and blasted out into the cosmos. It was a stunning confirmation of a long-held theory. This single merger event is estimated to have produced an amount of gold equivalent to several times the mass of the Earth. It proved that these cataclysmic neutron-star collisions are likely the dominant source of the universe's most precious metals. This discovery fundamentally reshaped our understanding of cosmic recycling. It means that the gold in a wedding ring or the platinum in industrial electronics was likely not forged in the heart of a single exploding star. Instead, it was probably created in the even more violent and exotic collision of two stellar corpses, the remnants of two separate supernovae that lived and died long ago. The universe, it turns out, has multiple breathtakingly powerful ways to enrich itself, ensuring that the cycle of death and rebirth continues to build an ever more complex and elementally rich cosmos. Every moment, the universe is quietly recycling itself. When we look at the stars, we see both the past and the promise of what's to come. The death of each star is not just an ending, but a cosmic beginning. The supernova's blast, the gentle puff of a planetary nebula, or the shattering collision of neutron stars, all scatter heavy elements into space. These ashes, drifting across light years, settle into cold clouds. From those clouds, new stars and planets are born, carrying within them the fingerprints of their ancestors. This cycle is the reason we are here. The calcium in our bones, the iron in our blood, the oxygen in our breath, all these elements were once locked inside distant stars that lived and died before our solar system even existed. According to recent astronomical surveys, an astonishing 97% of your body's mass comes from elements made in stars. Life on Earth is only possible because the universe is so good at reusing its own matter. Stars are both the creators and the destroyers in this story. Their lives are measured in billions of years, but their deaths last forever, in the sense that what they make is never truly lost. The elements forged in their hearts are given back, to be shared, reshaped, and reborn in endless cycles. The atoms that now make up your hand might one day shine in another star, or form the mountains of a distant planet, or even fuel life on another world. This cosmic heritage connects us to everything. It means that, in a real and physical sense, we are part of the universe's eternal story. Our existence is the result of countless cycles of creation and destruction, a lineage stretching back to the first stars. We are the living proof that the universe recycles, life from death and death for life. Cosmic recycling is not just a process, it's the grand choreography of the universe. Every star, every explosion, every atom obeys this timeless rhythm. As supernova remnants expand and mix with interstellar clouds, they enrich the cosmos with new elements, triggering the birth of the next generation of stars and planets. This process has unfolded for over 13 billion years, making the universe ever more complex and alive with possibility. Each new cycle adds to the richness of galaxies, to the diversity of worlds, and to the chance for life to arise. When we gaze upward, we are looking into a mirror of our own origins. The light from distant nebulae, the glow of newborn stars, and the fading embers of dying suns, all tell us that everything is connected. We are not merely in the universe, we are of the universe. Carl Sagan's words echo even more strongly as science reveals more. We are made of star stuff. To know this is to feel a profound sense of belonging not just to Earth but to the cosmos itself. The universe's recycling is not just physical, it's also a story of knowledge. We are the universe becoming aware of itself. Through science we trace the journey of atoms across time and space, and we see our own story written in the stars. Each discovery, each observation, is another step in understanding our place in this eternal loop. So, as you look at the night sky, remember the atoms in your body have traveled through stars, explosions, and space, only to become you. When we dream, wonder, and explore, we are continuing the universe's dance of creation and renewal. In the end, the universe is not just recycling matter, it's recycling possibility, hope, and life itself.